to distinguishing between types of intramolecular bonding. So I'm going to go ahead and put a caveat right there. So types of intramolecular bonding based on electronegativity. So again, key to determining the types of bonding is the valence electrons. So are they gained, lost, or shared? That's the key aspect here. So for van der Waals or a lot of intermolecular interactions, so we don't have this charge transfer here. So we have, again, the weak induced electric dipoles or permanent dipoles. So dipole interactions are essentially like, so we know that oxygen has a high electronegativity. And actually on our periodic table here, we could also find what is the electronegativity. So our electronegativity, our En on the Pauling scale, the larger the value, the more it wants to grab electrons. So you could see that for Na, it has a very, very low electronegativity because it wants to give up its electrons. But we can see for fluorine, 3.98, it really wants to hang on to and grab as much electrons as possible. It's greedy. So these dipole, if you have bonds, for example, like C double bond to O, oxygen wants to grab the electrons from here. So you could have these slightly negative interactions and dipoles occur. So we've seen that before. Again, and you get this, but for covalent bonds here, you have valence electrons that are shared between adjacent atoms. So, and repairing of electrons. So one covalent interaction you might have seen before is this one for polyethylene. So this CC bond is covalent. So is CNH as well. But anyways, exactly, pairing of those electrons in between those the valence, the electron shells. But if you have atoms that have different affinities for electrons, and if you have a large enough change in electronegativities, you can get a transfer of charge there. So you could form positively, negatively charged ions, i.e. cation, which is positive, anion, which is negative. This gives up electrons, gives up E, this takes E. Exactly, and you have this form these networks of ionic bonds. Again, so if the electronegativity is similar, however, the valence electrons are shared and the bond is purely covalent here. So let's start to kind of build up a list. So we have covalent, so ionic, and metallic. You can kind of say there's some properties. So I like creating some of these tables. So for En, electronegativity, we could also do for if electrons shared, and you can kind of describe a lot of these different values. So for covalent interactions, electronegativity is very similar or the same. So similar, same. For ionic, very, very different. Metallic is kind of a unique kind of character. So we'll get to this in the kind of the last section. So the electronegativity is very, very, very different. The more electronegative will basically take out, withdraw almost all of the valence electrons, and that bond will be purely ionic. So electronegativity is going to be how we're going to distinguish between covalent and ionic interactions. That's kind of the critical nature here. So you might ask, well, if it's based on electronegativities, what's the critical difference that determines whether something is covalent or ionic? Well, the problem there is there's no unique kind of pure textbook or kind of agreed upon definition. And actually, the true answer is there's very few interactions that are purely covalent or purely ionic. Usually they have some characters of both. So it could have some covalent character and ionic character, characteristics. And these will be polar covalent interactions. So again, still interatomic interactions, or intramolecular interactions, but they'll have natures of both. So in this class, again, no universal agreed cutoff values of electronegativity differences, but if the electronegativity difference is 0 to 0.4, it is going to be nonpolar covalent. So 0 to 0.4 nonpolar covalent. I'm going to add another one here. So polar. If it's between 0 and 0.5, 1.7, that is going to be polar covalent here. And then greater than 1.7, that is going to be ionic. So here, again, electrons are shared. Here, they are taken away. So taken. And this is like in between our Goldilocks. So these, again, there's some directionality to kind of covalent interactions as opposed to some of these other interactions that we're going to deal with. And finally, let's get to our case of metallic. In metallic bonds, all atoms share their valence electrons. And they basically, you form these nuclei that are positively charged in this array of delocalized electrons. So delocalized means that they're just kind of everywhere. In polar, usually we think of, here's our nucleus, and then we have the shells of electrons, right? And they're confined to these shells. And actually, as you can see in this kind of figure here, we can see that this is kind of showing here, the electrons for metals, they can kind of just fly around everywhere. And this makes sense, right? Metals are good conductors of electricity. That requires electrons to be delocalized. They can't be kind of stuck like here for covalent interactions. They're kind of localized to these. There's still some directionality to it, but they're localized. For ionic, one grabs, one electron, so they're kind of taken as well. And then there's the fluctuation of those dipoles. But again, that's the unique nature of metallic interactions. They're delocalized, and that leads to kind of the unique electrical conductivity ideas. So again, van der Waals form covalent interactions, and they have some net or induced dipole, very, very short range bonds between neighboring molecules, between intermolecular. So again, they lead to kind of cool phenomenon, gecko pads, graphite sheets, water, polymers, proteins. Van der Waals are super, super important and very, very important. And we'll get to that in lecture 9 in our polymer lecture. All right. So next time we're going to do a very, very brief lecture on hybridization and then get to a really, really cool topic, which is isomeric states. So we'll see you then. All right. I'll see you all in the next video and in lecture. Bye.